the fundamental theorem of calculus. Okay, now this comes in two parts. The first part is that if you have a function like this, if f, or rather, if f is continuous and g is defined to be the integral from a to x of f of this continuous function f of t, then this function will be continuous and differentiable, and the derivative will be equal to f. The derivative of g will be f of x. Okay. More generally, you have this as well, and this comes from two things. This is basically just applying that, but there's the chain rule is one aspect of it. Okay, that's how you could get, if it was like from a to h of x. Okay, so if you just had a constant here and then an h of x up here instead of a g of x, then you basically would apply the chain rule with this and with this idea, and you get that piece. And then for the bottom part, so this is from the chain rule, and the bottom part, this part right here, which comes from this function on the lower limit of the integral, that would come from this fact right here, that if you take the integral from g of x to h of x, that's equal to the integral from g of x to a. Well, you can just find some number, some constant between them, plus integral from a to h of x. And then this one right here, it's equal to the negative of going from a to g of x. Plus that. Okay. So this integral here is just the negative of, if you reverse the order, these limits, then you get, and it's the negative of the corresponding interval. Okay, if you integrate the backwards. Okay, so that's the theorem part one, and this is probably the most general. This is probably the most general form right here, which would be useful. But there's also this simple way right here where you just like, this is really simple, supposedly. Okay, and then there's this part two, which is probably what you're going to be using a lot more, and that is to find a definite integral where you're integrating from a constant a to a b, an a and b are constants. Then you find any antiderivative of little f, any antiderivative of this, and you get this. Now the notation is like this. So when you're actually doing an exercise, what's going to happen is you're going to find an antiderivative. Okay, and you're going to have like that. And then you're going to put a line right here and from a to b, like that. And that means, okay, so you find an antiderivative of this, and you put this there. And then the next step would be to substitute the upper value in, subtract, and substitute the lower value in. Okay, which is just basically what we have right here. So, but usually people will put this intermediate step here. It just kind of helps to sort through what's going on, rather than going directly from here to here. Find an antiderivative in x with the variable in there, and then put the values in later. Okay, so that's the way to do it. Okay, so let's get to some exercises, and then number one is to kind of help us to understand the concept. And we have this function g of x is the integral from 0 to x of f of t. Here's f. This is f, not g. G is the integral from 0 to x. So here, g of 0 will be the integral from 0 to 0 of f of t, which if you take the integral from this, if the upper and lower limits are the same, then this is just going to be 0. Okay. And g of 2 is going to be the integral from 0 to 2 of f of t. And if you look at that, so you're integrating from 0 to 2, then that's going to be this area right here. And this area is, it's a triangle, so it's 1/2 the base times the height, or the base is 2, the height is 2, so that's going to be 2. So that second answer is going to be 2. Okay, now let me, the third one, g of 4. Okay, let's do this one over here. So g of 4, that's going to be the integral from 0 to 4 of f of t dt. Okay, so that's going to be going from 0 to 4. So you have this area here. You also have this area here, but this is under the axis. Okay, so I guess that we can label these areas. Maybe we can label that one as 1, and this is 2. That one is 3, and then 4, 5, 6. So that's going to be that's going to be area 1 minus area 2, which those are going to be the same. You can see that this was going to be also as 2 right here. That's just going to be 0. Or I guess it's 2 minus 2 or 0. Okay, so you can see that this area here is going to be 2. So that's going to be 0. And then g of 6. That's going to be an integral from 0 to 6 of f of t dt. So that'll be 1 minus 2 plus, or let's see, minus 3. This area right here. And this is also going to be 2. So that's going to be negative 2. Okay. Now we have g of 8. Okay, so that's going to be integral from 0 to 8. And 1 minus 2 minus 3, and then it's going to be plus 4. This area here. So that's going to be 2 minus 2 minus 2 plus 2, where it's going to be 0. Okay, so g of 8 is going to be 0. And then we have g of 10. That's the integral from 0 to 10 of f of t dt. And you're basically going to get all of this, all of these, plus area 5. And area 5 is, let's see, area 5 has got this part right here, which is 4, and that's 2. So that's 6 then. Okay, so that's going to be 6. And then finally, g of 12 is the integral from 0 to 12 of f of t dt. So that's going to be g of 10 plus area 6. And area 6 is 4, 4, and 2. So that's, so all of this is 6. And then we have, what is it, 4 and 4 and 2. So that's 10, 16. Okay, so that'll be 16. And then part B, we're supposed to estimate g of 14. So estimate g of 14. So it's going to be equal to g of 12 plus this area here. We'll call this area 7. And this looks like about 4. This looks like maybe, this is less than 4 actually, because you've got a little area here. This is also less than 4. This one is, that's going to be less than 2. So 4, 4, 4 and 4 and 2 is what, 10? Maybe a little bit less than that. So maybe 9. Okay, maybe this is going to be 9. Maybe 9. So maybe I should write it like this. This is area 7. So that's going to be 16. This is 16. And then that's about 9. So 25. 25 should work, the answer. Probably if you a little bit more or less than that is probably also going to work. Okay, let's look at numbers at part C. And it says, where does G have a maximum value and where does it have a minimum value? Okay, it looks like it was a maximum when you were at 14. So over here was the maximum value. And the minimum, it looks like at 6 it was the minimum. So right here, because at 6 you've integrated this part here, but then you've integrated all this negative part. Okay. They're very tricky here. I don't know if you noticed, but they say max. Where did you have a maximum? And then after that they ask where does it have a minimum? But then they reverse it. Here, look at that. How tricksy. They put minimum and then maximum. Whoa. I mean, they should have reversed these two maybe. Oh well. Okay, now the next thing is to sketch the graph. And so maybe, we can just plot a few points to kind of see what happens. So at 0, it's 0. At 2, it's 2. It's up here at 2. We'll call that 2 right there. Although maybe I should put that a little lower because there's a 25 there. Here, in fact, let me do this. We'll sketch it in black. Okay, so it seems to be, yeah, right there. Okay, so let's say that's 2 right there. And let's say this is 2 also. Okay, so at 0, it's 0. And then it goes up to here to 2, right? At 2. And then at 4, it's back at 0. And then at 6, it's at -2. So you're down here. And then at 8, you're back at 0. And then at 10, you are up at 6. So you're up here. And then at 12, you're at 16. So you're way up here. Okay, so it looks like it goes something like this. Oh, and then at 14, it's at 25, it's even higher. So it's something like that, okay? So that's what G is going to look like. And it's the third one. The third graph is what it looks like. Or you can compare this one with what's in the Webassign. Okay, great. So that just gives you an idea of what this kind of function is. And then keep in mind that the first theorem, the part 1 of the fundamental theorem of calculus is telling you that the derivative of g of x is just f of x in this function. So the derivative of this function is just this function. And you can kind of see that right here. This is a local maximum, local minimum. And those are precisely where this function crosses the t-axis or the dependent variable axis right here and here. Okay, so that's kind of interesting. Okay, let's move on to number 2. Here we have, you're taking g of x is the integral from 1 to x of t squared dt. Okay, so here we have a function, the function is t squared this time. And that's our little f. Little f of t is t squared. So what I'm going to do, we're supposed to sketch the area represented by that. Okay, so what you do is you can sketch y equals t squared like this, okay? Okay, then you're going to put, this is the integral from 1 to x. So what you do is you say, okay, that might be 1 right there. And that's where the graph is right there. We'll draw a vertical line right there. And then x could be something over here, but x is variable, so it could be actually anything. It could be back here too, but let's put it to the right, okay? Because you want to go from a lower number to a higher number. And so x is a variable, but let's just put it right there, to the right of 1. And so g of x will be the area. This will be this area right here. And now if x moves a little bit further, then this area is going to get larger. If my x goes that way, then this area is going to get smaller. And so it looks like the third graph again. Okay, so that's kind of what this function represents. Okay, and then part 2, we're supposed to find it g prime in 2 different ways. First one is by using the fundamental theorem of calculus. Okay, so basically what that said was just take this t squared and replay and make it just to an x squared. That's it. That's all. That's all you had to do. That's it right there. That would be the answer right there. And then part B is to just evaluate the integral using part 2 of the fundamental theorem of calculus and then differentiating. Okay, so the second way would be like this. Let me just copy this down. Okay, so basically, I said the steps are to find an antiderivative of this. Okay, to find an antiderivative of this, and that would be t to the third. Now, well, not exactly, but if you think of t to the third, if you take the derivative of this, the 3 will come down, and this will be a 2. So you'll have a t squared, yay. But you have this 3 to deal with, and you just divide by 3 to get rid of that. Okay, so now think about it. If you take the derivative of this, you'll have a 3 coming down. That will cancel with this 3 here, so the 3's will go away, and this will reduce by 1. 3 minus 1 is 2, and you'll just get this. Okay, now I said put a line right here with the lower and upper limits of the integral. Then the next step is to plug this into here for t, subtract and plug the 1 in. So 1 cubed is just 1 over 3. Okay, so this is what g of x is. Okay, g of x is just this. It's x cubed over 3 minus 1/3. That's what the function is. Now it says differentiate, because you want to find g prime of x, right? So you differentiate this. 3 comes down. That reduces with that 3, and you're left, and this reduces by 1, and then this is 0. Okay, so you get the same answer as you got from the first part. Either way, the second part was a little bit more work though. Okay, so number 3. Find the derivative. Okay, you're integrating from 4 to s. So this is a constant. This is like a. Okay, so remember, so essentially you're integrating from a constant to s. So you just replace these t's with s's and you're done. G prime of s is this. S minus s squared all raised to the 6th power. Okay, number 4. Find this derivative. And this one, like I said, is using the chain rule. So this goes in for the t. That's an e to the x. So this e to the x goes into here. So you have 4 log of e to the x. And then you multiply by the derivative of e to the x. Okay, so this one is the derivative of e to the x. Okay. which is just e to the x. Derivative of e to the x is just e to the x. Okay, so this is going to be your answer. However, log of e to the x is just x, so so you just get 4x e to the x for that one. Okay, again, this is just going back to, let me refer you back really quickly. I'm just using this formula here, but I have a constant on the bottom, so that means that this term, when you take the derivative of a constant at zeros, that means this term goes away. Okay, so I'm just applying this, or if you want to just apply this and use the chain rule, that's fine too. That works as well. Okay, let's do another one of these. Okay, now this one, again, these two are going to use the fundamental theorem of calculus part 2, which is this one, which you're going to go this route. You take your limits of integration are constants, and you just want to find this. Okay, so so you're going to find an antiderivative, and then so on. Okay. Okay. So basically, we want to find an antiderivative. So I'm going to rewrite this as x to the 1/2, because now I'm more confident about finding an antiderivative. And if I raise this by one power, so 1/2 plus 1 is 3/2, right? Then when I take the derivative here, I'm going to end up with x to the 1/2. But I'll also have this 3/2 coming out. So I just counter that with a 2/3. Now when the 3/2 comes down, we're prepared, and the 2/3 just cancels with it. Okay, so the derivative of this is x to the 1/2, which is square root of x. Okay, then I put the limits right here, 1 and 4. And okay, I'm going to plug in, I'm going to plug in the 4 first. And then subtract and plug in the 1, like that. Okay, then 4 to the 3/2. So if I do the 2 first, then that's the square root of 4 is 2. 2 to the 3rd is 8. So this is going to be 8. And that's just going to be 1, so that's 2/3. Okay, so we got 16/3 minus 2/3, that's 14/3. Great, so let's do the next one. Here, the best way to do this one is to split up into 2 pieces. Okay, so you have 4 over the square root of x plus x squared over the square root of x. Okay, 4 over the square root of x is the same as 4 times x to the negative 1/2. This one is x to the 3/2. Okay, so 2 minus 1/2 is 3/2. Okay, so now we're ready to integrate. This one, if I add 1 to this negative 1/2, I get x to the positive 1/2. Okay, now when I take the derivative of this, sure, I'll get this will be part of it, but I'll have this 1/2 coming down. So I need to have, so if I put a 2 here, then it will eliminate it, but I need a 4 there, so let's put an 8. Okay, so now if I put an 8 there, 1/2 comes down, 8 times 1/2 is 4, so I get the 4, which I needed. Here, raise this by 1, put 2/5 there, so now when the 5/2 comes down, it cancels with that, and we just get this. Okay, so I don't know why I wrote that. Or maybe I didn't. I don't even remember writing it. I probably didn't write it. It probably just appeared out of nowhere against my will. Okay, so put the 4 in, so that's 4 to the 1/2 plus, and put the 4 in here also, 4 to the 5/2. Okay, that's putting the 4 in. Now subtract and put the 1 in. So I put a 1 in here. Actually, I don't even have to write it. When I put the 1 in, it's just going to be 1. So I'm just going to go ahead and simplify that. Since that one is that. Okay, now let's see. 4 to the 1/2 is 2. 8 times 2 is 16. And then here, this is 4 to the 1/2 is 2. So 2 to the 5th is, whoa, 32. 32 times 2 is 64. Then we have a -8 minus 2/5. Wow. And that turns out to be 102 over 5. Let me simplify that out. That's a 5. That's a 1. Let me write that better. Okay. So 102 over 5. Okay. Now, let's go to number 7. We're supposed to evaluate this integral, the integral from 0 to x. No, 0 to pi. That's a pi. That's a pi. That's a pi. Where f of x is, it's sine x if x is between 0 and pi over 2, and it's cosine x if x is between pi over 2 and pi. So f is not a continuous function, but it doesn't matter, because to handle something like this, what you need to do is it's defined one way between from 0 to pi. So here we're taking the integral from 0 to pi, but on the first half of that interval from 0 to pi over 2, it's defined one way. It's defined as sine x. On the second half, it's defined a different way. But integrals can be split up like this. You can split it up on the interval and take it on part of the interval and then the other part. No, that's perfectly fine to do that. Okay, so you split up into 2 integrals like this. Okay, now from 0 to pi over 2, where you're integrating here, it's just sine x. Okay, so you put a sine x in here. And from pi over 2 to pi, it's just cosine x. So you replace this f of x with the cosine x, like that. Okay, now it's time to apply part 2 of the fundamental theorem of calculus and find an antiderivative of sine x. That's going to be, well, cosine x seems like a good candidate, but when you take the derivative of cosine, you get negative sine. We want positive sine, so just stick a negative on the front there, and we're good. And now it's going to be evaluated from 0 to pi over 2. Then over here, sine x. If you take the derivative of sine x, you just get cosine x. So this is going to be sine x, and that's going to go from pi over 2 to pi. Okay, so we go to here first, plug in pi over 2, so that's going to be negative cosine of pi over 2 minus negative cosine of 0. And then over here, you plug in the upper limit, so that's going to be sine pi, subtract, and plug in the lower limit, pi over 2. Okay, now cosine of pi over 2 is 0, so that goes away. Sine of pi is also 0. and this is going to be positive cosine of 0. So this is going to be 1. And this is also 1, but it's minus 1. Okay, so all that work for getting 0 as the answer. Okay, let's go on to number 8. And what we're supposed to do here is sketch the region enclosed by these curves. Y equals 4 minus x squared, y equals 0, and y equals 0. Okay, so by those two curves there. Okay, so let's go ahead and then also calculate its area. Okay, so this right here is a parabola that opens downwards. When x is 0, we're at 4. So it should, if that's 4, it should go through there. And then open down, that's the vertex. And if you set this equal to 0, you get plus or minus 2. Okay, so it's going to go through at 2 and to negative 2, like this. Okay, so it's going to be a parabola going like that. And what the? Hold on a second. Okay, so it's going to be a parabola like that. And let's see here. And then y equals 0, of course, is this right here. And so the area, okay, so sketch the region enclosed would be all of this right here. This region there. And it looks like the third one is the correct answer. Okay, and then we're supposed to calculate the area. Okay, so the area, that's going to be the integral from -2 to 2 of this function, 4 minus x squared. That's going to be the area. Now, you can sometimes exploit these kind of things if you want. You know, if you don't want it, that's fine. But we could calculate the integral just like it is. But also, what you could do in this particular case is you notice that this is all symmetric. And this area, let's say that's area 1, and let's say that's area 2. So area 1 equals area 2. Both of those are both this area and this area are equal to each other because this is all totally symmetric here. So that means that if we want to, we could, instead of calculating from -2 to 2, we could go from 0 to 2. We could only calculate this area and then double it. Okay, so that's a perfectly fine, a reasonable thing to do. And it helps to save a little bit of time in a lot of cases. Okay, to do that. Okay, so now the idea is to find an antiderivative of this. So 4x would be the antiderivative of 4, and then this one is x cubed over 3. Because when you take the derivative here, you'll have a 3 coming down, which will cancel that 3 off, and then we find, we'll have a negative right there. And then derivative of this is 4. Okay, and then 0 to 2. Okay, so now the reason that we put the 0, so hold on. Okay, so put the 2 in, and we have 4 times 2 minus 2 to the 3rd over 3. Then subtract and put the 0 in, and then here's where it's nice where you have the 0, because then when you put the 0 in, it's just 0. Everything's just 0. Put a 0 into there, the whole thing zeroes out. Put a 0 into here for x, and everything, this all is just going to be 0. Okay, so we have, what is it, 8 minus 8/3. So that's 16/3. Okay, so 32/3 is the area. Okay, let's look at number 9. Evaluate the integral and illustrate with a sketch. Okay, so let's do a sketch here. This is x cubed, okay? So x cubed, it comes up like this. Oops. Flattens out and then continues on upwards like that. Okay, and let's say that's -1, let's say that's 1, and then 2 could be somewhere over here. Okay, so from -1 to 2, you have this area here, and then from 1 to 2, you have this area here. Okay, so this is what the sketch is going to look like. So basically, this integral will be this area minus that area. So all this area up here minus all that area. Okay. So let's go ahead and calculate this integral. So we find an antiderivative, which is, if you consider x to the 4th, when you take the derivative here, you have a 4 coming down. There's no 4 there, so let's get rid of it. Let's get rid of it by putting a 4 in the denominator. Now when the 4 comes down, we're ready. Okay. And that's going to be evaluated from -1 to 2. So if you put a 2 in, you get 2 to the 4th over 4. Subtract and put a -1 in, you get that. So this is 16 over 4. Now you're tempted to be like, just turn this into a 4, but resist, please. Resist the temptation. Okay, so you have 16/4 minus 1/4. That's going to be 15/4. Okay, so now you see why I told you to resist the temptation. Okay, it's usually a good thing to do that, but in this case, it's better to leave it like that, and then, because you'll have to go back to this anyways in order to subtract this 1/4 from it. Okay, that's number 9. Another way that's interesting here, let me just point something out right here. Another way that you could have done it is you could have said this is the same, because like this area and this area are going to be the same, right? These two areas are going to be the same. And then this is negative area, this is positive area. So they're just going to cancel each other out. So you could have said, oh, this is just the integral from 1 to 2 of x cubed dx, and just calculated that. It would have been exactly the same, except you'd have just a 1 right here. And then, because when you take this to the 4th power, it goes away anyway. So you just get the same. It'd be basically the same calculation. Okay, so that's another way you could do it. Okay, this is alternative. Okay, especially because you see the graph right there. Okay, let's look at number 10. Finally, number 10. Okay, so this right here was the general form of the first part of the fundamental term of calculus. Right here, this is the general form. It's applying the chain rule and also the other trick that I showed you. Okay, here we actually, number 10, we actually have the lower limit is a function and the upper limit is a function. We're supposed to find the derivative. Okay, so this is dy dx. This is a function in x because there's v's here and it's dv, but this doesn't really matter what variable this is, because basically if you're just going to calculate this, which it'd be kind of a pain to calculate, if you're going to calculate this, then when you would find an antiderivative for this, they would be in v's, but then you would plug for v, you would substitute this one and then subtract and substitute that in for v. So in the end, you'll have just x's if you were to evaluate that. So it's really a function in x. Okay. So according to this, you plug in the sine x into here. So this sine x goes into there. And then you multiply by the derivative of the sine x becomes an inner function. You multiply by the derivative of that inner function, so that's cosine x. Okay, subtract, put the cosine in, multiply by the derivative of cosine, which is negative sine. And that's it. And that's it. That's it. So this is going to be the log. Oops, this is not the best written. Log of 3 plus sine x cosine x minus, or no, you have a minus here, the minuses cancel. Okay, that's why I rewrite the whole thing instead of just leaving it like that, by the way. 3 plus 5 cosine x times sine x. Okay, and that will be the answer right there.